Hello guys, this is Mr. Y. Today we're going to be talking about learning the differences between observation and inference and understanding the different parts of experimental design with the following vocabulary: hypothesis, independent variable, dependent variable, experimental group, control groups, constants, and the difference between results and conclusions. Okay, so these two pictures here I like as a comparison because they do a good job illustrating the problem with understanding observation versus inference. You can see the drawing on the left is supposed to be an accurate representation, but in fact is not, of an actual giraffe. Now, I'm not trying to knock the artist's skill level. He's definitely a good drawer, but you can clearly see that the observational approach to the anatomical features of the giraffe, say up here at the head where these horns are, and even the shape of the face overall, is clearly not accurate to the actual anatomy of the giraffe. And you can even see some problems with the body, the way the body plan is shaped, and the scale as well, because according to this scale, the person here only goes up to a giraffe's knee, which in reality a person would probably be maybe up to the middle of this top leg up here. So understanding the difference of observations versus inference was a big issue in science for a long time, because for a long time there was no such things as photographs. And so observations were always taken to be truthful, though you had to be somewhat skeptical of this because you can see why somebody might misinterpret something. So understanding the nature of the difference between an observation and an inference becomes really important in making new discoveries. Remember that observation is one of the two ways that we can make truly new discoveries in all of science. So let's talk about what an observation is. An observation is receiving knowledge from the outside world through your five senses. Of course, sight, sound, taste, touch, and smell. You could also count observations as anything that you can record using an actual instrument. So anything like a telescope, a microscope, a Geiger counter that measures radiations, things you can't normally see or taste or touch or smell, but you can make them measurable in some sense through instrumentation. Those count as observations as well. So you have your senses for observation, but we also have in science instrumentation to allow us to do observations as well. And this is in contrast to an inference. An inference is not an observation. An inference is reaching a conclusions based upon facts or knowledge. It's essentially to make an educated guess. Whether your inference is correct or incorrect, that can be up in the air. It can be up in the air for quite a while. So observations, nobody really likes to argue about because they're so blatantly obvious. Anybody can observe them, hopefully. Inferences are people can make arguments where you can say, okay, I don't think this inference is correct. I don't think your conclusion is correct based upon the facts because maybe you've seen different data. So let's try and peel these two things apart from each other using an example here. Here is a cartoon. I like using cartoons for illustrating the difference between observation and inference because oftentimes humor comes from making inferences based upon observations. So we can observe, for instance, in this cartoon, several things. Again, it's a cartoon, it's visual, so all our observations are going to be visual in the sense. But we can observe, for instance, that there's a bird in a cage up here. We can observe that looks to be an old style checkout machine. There's a counter here, obviously. There's a window with some writing on it. The writing looks to be reversed, as in, I think the writing, and this is, we'll get to inference in a bit, but it appears the writing is backwards. There's a bowl of water here with a fish in it, and there's a sign on the bowl that says piranha for, what's that, almost $30, $29.95. And there's a cat here. And then all these things are observations because nobody's going to argue that any of these things are there. You're not going to say, well, there's not a window, there's not a bird, there's not a cat, there's not a fish, there's not a cash register. Those are observations. Again, nobody likes to argue about observations. Inferences are educated guesses based on observations. Well, let's make an educated guess about what's going on here. Again, this is a cartoon. It's meant to have a bit of humor to it. Well, you can see in the window, as I noticed, the lettering looks backwards. Well, the reason the lettering is probably backwards is because the writing would probably be on the outside. And on the outside, if you were to read this the correct way, it would say Bob's Pets. So this looks to be with that sign and this cash register here, perhaps a pet store, because we have seen 3 different animals here that would fit the qualifications of what you might consider a pet. You can also see that there was a for sale sign here, so that would make sense to go along with this idea. So you have 3 pieces of evidence, 3 observations that support this inference that this is a pet store. But again, this is meant to be a cartoon, so there's got to be an aspect of humor to it, and that's where you can go back to observing the cats. And if you look closely at the cat, you can see there's something off about the cat's front legs. You can see they're not actually front legs. They're actually 2 wooden sticks. They're little peg legs on the front of the cat. And he's like, okay, why would the cat have peg legs? Well, let's observe a little bit more about the cat. The cat appears to be looking directly towards the fish over here. And so you can make the inference that, oh, well, maybe the cat got a little too frisky with trying to get to the piranha in the fishbowl and didn't realize it's a piranha, not a normal fish. Piranhas don't actually eat things that fast, by the way. It's just a cartoon thing. But you could make the inference that the reason the cat lost its legs and has 2 peg legs now is because it was messing with the piranha. Now, maybe we're right, maybe we're wrong. Maybe the cat just had some problems with its legs and that's why it doesn't have its front legs. Again, inferences can be argued about. The fact that there's this fish, a cat, a bird, a cash register, a window here, those are observations. Nobody likes to argue about those because they're clearly obvious. They tend to be considered almost factual. So observations are what you know to be true. Inferences are what you assume to be true. That's how you can tell the difference. If you can know it to be true where nobody's going to argue, that's an observation. If you're assuming it to be true, somebody might come along with a different argument based on different facts. So those are the 2 questions you want to ask yourself with this stuff. What is it you know to be true? What did you know to be actually happening? And what is it you are assuming to be happening when it comes down to separating observation versus inference? Here's another example. This is from the cartoon Calvin and Hobbes. This is Calvin here. He's a very mischievous little boy. I'm just going to read off what he says. He says, "For show and tell today, I have something that will astound and amaze you. This little guy can," and then you can see he is, and I'm making an observation here, he's looking down into the bag. You can see, based on this drawing, it looks like he's looking around. And then he says the following on the last slide here. He says, "Have you all had your shots?" Now, observations, again, what you know to be true. Well, in the second slide, he's definitely looking in the bag. In the first slide, he clearly has the bag. The bag appears to be rolled up. And he's clearly talking. And from the sounds of what he's saying, you know, you can observe that he's talking about show and tell, and he says he has something that will be astounding and amazing, and he says this little guy, as if he's referring to something that's perhaps alive, looks down and he starts looking around. These are all observations. I'm not inferring anything here. And then his last comment, "Have you all had your shots?" Again, this is a comic strip. It's meant to have an aspect of humor. So Calvin, being a very mischievous little boy, the inference here would be that Calvin had brought some little critter in, you know, who knows what, in this little bag. He opened the bag right here to look in, to find it, to reach it out as he was talking, and realized, oh, it's not in the bag. And he starts looking around for it, and he immediately realizes he doesn't know where it is, and he's worried about his classmates. So he asks, "You've all had your shots, right? In case you've been bit," being the subtextual comment coming next. So again, observations, what you know to be true. We know Calvin's talking to somebody. We know he has a paper bag that he looks in it, he looks around. Inference is what you assume to be true. Now, could we be wrong about this inference, that maybe Calvin didn't have a little guy in there? Maybe Calvin's actually playing a joke on his class? Possibly. He's almost smart enough, if you read his comic strips, to pull that off, where he would bring out just an empty paper bag and just pretend to look in it. It's possible. Again, that's an inference. It could be right, it could be wrong. Again, what you know to be true is an observation. What you assume to be true, that's. And for one final example of observation versus inference, this is another strip of Calvin and Hobbes. This is Calvin talking to his dad, and he says, "New hat, Dad?" Dad turns to him and says, "Yep." And he says, "I like it." And Dad says, "Thank you, so do I." And then you see Calvin here, and then you hear this text box, and you don't actually see either of them in this last text box. All you hear are these words. I know it's a visual thing, but you can take it for hearing. It says, "Ah, you're going to be late for work, Dad." Now, let's try and piece apart observations from this. First, you can observe several things. First of all, you can observe the environment, that there's a tree in the background right here. You can observe that Calvin looks to be dressed in his kind of winter gear. Dad appears to be dressed pretty warmly as well. And they're commenting on Dad's hat up here. Calvin says he likes the hat. That's an observation. Dad says, thank you, so do I. And then this third one, we have another observation. You can see that it looks to be Calvin, he's not on the sidewalk. You can see Dad's on the sidewalk. Calvin's kind of off to the side of the sidewalk, kind of where there might be grass, but there's no grass. And that's where you notice, oh, Calvin right here is actually in the process of making a snowball. And over here on the last slide, well, what do we observe? Well, there's the words, of course, but we also observe, well, there's Dad's briefcase, there's Dad's new hat, and then there's this stuff of snow right next to it. So again, humor tends to come about from making inferences, things you don't necessarily see and trying to figure out what's going on. So what we can kind of infer about what's going on here is that Calvin, making comments on Dad's hat back and forth, pointing out, oh, it's a new hat, and he says, I like it, and made himself a snowball. And then what did he do? He actually pegged Dad's hat off his head. And then what did Dad immediately do? He dropped the suitcase and started to chase his son. And his son, recognizing that his dad's now chasing him, was trying to say, Dad, don't come after me. You're going to be late for work. That's the whole purpose behind this text box here. So again, that's an inference. Could we be wrong? Yeah, it's possible we're wrong somehow. That maybe that's not exactly what happens. But we didn't actually observe what happened. So there's slight other possibilities. That seems the most logical to me. And so it's probably right, but it could theoretically be wrong. There could be some other explanation I'm just not thinking of. So again, we know the basics. We know the basic facts of what was going on. We don't know exactly what happened in that last, panel thing there. That's an assumption, not an assumption, an inference, an educated guess based on observations. So I hope it's a bit clearer now on the difference. Again, what you know to be true, those are observations. What you assume to be happening or have happened in the past, those are inferences. Those can be argued about. Nobody likes to argue about observations. So we're going to switch this over to talking about one of the other ways in science that new things can be truly discovered, that being experimental design. I know I've talked about experimental design versus observation in a prior lecture, but now we're going to get into the nitty-gritty of how experiments are designed to work. And in many cases, they don't work at first. So it might take a while to get the hang of how to design a good experiment. And in this case, this right here would be a very bad designed experiment. So yeah, it takes practice. There's no getting around that. You cannot expect every single experiment you ever design to work perfectly. And in fact, if you do get an experiment to work, oftentimes it tends to be a fluke. Like trying to repeat good experiments tends to have real problems on its own. So getting just the knack for how to design an experiment to work the way you want it to work is one thing. And then actually learning if the experiments supported your ideas or rejected your ideas, that's a whole nother thing. But we'll get into the nitty-gritty of the different parts of this. So we're going to start with the hardest part of any experiment first, that being the hypothesis. This is the crux of the entire experiment. If you get this wrong, it doesn't matter if you do everything else right, your experiment's not going to be good. A hypothesis must have certain qualities. First of all, it must be specific and testable. That is to say, you must have a very clear thing that you're trying to focus on. You can't be vague about it. You can't be general or generic. You have to be very, 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 very specific and with what you're testing. And what you're testing must actually be testable. That's to say, you have to be able to get some kind of measurement out of whatever you're setting up. If you can't get a measurement out of it, so when I say testable, I mean measurable. When you can't get a measurement out of it in some way, shape, or form, it's not testable and it's not science. And it's looking to see what the relationship is among things. Like, is there a connection between two things, or is there no connection? Sometimes that can be a hypothesis too, that there's two things that people assume are connected, and in fact, they're not. So You can kind of think of a hypothesis like a prediction, again, but it has to be specific and testable. And if it's a really good hypothesis, a true scientific hypothesis, it must be for something that's going to happen, you think. You can't make hypothesis based on past events. That's more of an inference. And what we would call conjecture. So usually for designing experiments, you want to be able to set up a system to where you make a hypothesis for something that's going to happen in the future. That's measurable and testable and specific, that will occur when something is changed and messed with a little bit. Remember, if it's not clear or specific with your prediction, or if it's not testable, it's not science by definition. If it's too vague, that's wrong. If it's not specific, that's wrong. If it's not measurable or testable, that's wrong, and it's not science. So that's how you can usually spot bad science from good science. If it's either unclear in what it's trying to establish relationships, right? It's not a specific prediction, and somehow it's really like messing up the measurements. Well, like there's nothing really specific coming out of the measurement system. You're not seeing clear results in terms of what actually is being recorded. So I'm going to give you some very basic examples that you probably are familiar with in terms of format-wise from middle school. This would be an if-then example. For instance, if plant growth is related to the type of soil that the plant has, then exposing plants to unhealthy soil will result in changes in plant growth. That is pretty specific, and it is testable, and it's using this format called if-then. Again, that's usually the standard format the middle school teachers will teach you, and I expect most of you have seen something like that. If you change this, then possibly this is connected to it. Here's another example. If skin cancer is related to ultraviolet light, then people with a high exposure to UV lights will have different rates of skin cancer. Again, specific and measurable. You wouldn't, set up an experiment when you do this, but you could look at research to see if you could find a correlation between those exposed to high amounts of UV light and what their rates are of skin cancer. These are, again, basic if-then hypotheses. I expect you're familiar with this, but prior to this video, you should have watched a different video, not from me, but from somebody else, explaining the three types of basic hypothesis. The if-then style versus what's called correlation or effect style versus the comparison style. You should watch that video. If you have not watched it, go pause this now and go back, because everything from this point forward is not going to make sense to you as I explain hypothesis. All three of these styles, and again, you're probably more familiar with the if-then rather than the other two. All three of them are good and have their strengths, but we're going to try and elevate you guys a little bit in making your hypothesis. So make sure you're clear with what these three are, because the next part is going to be based on understanding those three styles of hypotheses. They each use different wording, so obviously the if-then uses if-then. The correlation uses the phrase, this will result in, and the comparison uses obviously a comparison style where it says compared to. So what I decided to do to help elevate your style of hypothesis, and you'll see this in the next slide, is actually combine all these into what I call a blended hypothesis. So again, make sure you've previously watched that video on the three styles of hypothesis format. Otherwise, what I'm about to show you is going to make very little sense when we blend them all together into one format. So this blended hypothesis is going to use the following key terms, which I have taken from all three of those basic styles of hypothesis. The if, then by, this will result in, and compared to. And they're going to go in this order. The if section is where you're going to put what do you think is causing what. If A is causing an effect on B. So in general, what is causing what? We're not being very specific here. We're just saying we think this is having an effect on this, cause and effect. Then by, and this is where we're going to state what exactly we are changing, or what is being changed in the experiment, and how is it being changed. You could use words like increase, decrease, remain the same. That's the best approach you could take. Sometimes you can't always do that, but if you can, you'll work in the words increase, decrease, or remain the same. Always, I recommend doing that. It makes you sound much smarter. The third step, this will result in. So when we made our changes, this will result in, well, what effect will this have? And how is that effect going to be measured? You would use units here. Are you using pounds? Are you using feet? Are you using centimeters? Are you using miles per hour? Are you using seconds? What is your unit of measurement? What exactly are you measuring? How are you measuring it? And we're going to make that measurement in comparison to our control groups, our comparison groups. And I'll clarify that a bit later on, but it's basically your baseline. What are you comparing your results to show if there's actually some kind of effect going on here? So here's an example, and I'm going to use that same if-then idea that I showed you on the last one about plants and soil quality. So if soil quality affects the rate of plant growth, notice I'm being very general here. I'm not saying how it affects it. I'm just saying if soil quality affects the rate of plant growth, then by growing a plant in a pot of low quality soil, so this is what I'm changing, and because I said low quality, you can see exactly how I'm changing it. This will result in the plant having a decrease in height in centimeters after 12 weeks of growth compared to the height of the same species of plant grown for 12 weeks in high quality soil. So again, the if, what do I think is affecting what? Then by, what am I changing and exactly how am I changing? I'm in this case changing the soil, and you can see here I said low quality, so I'm lowering the quality of the soil. I would say decrease quality of soil in some cases, but that seems overly wordy. And the effect I expect, again, number 3 is my prediction. This might be right, it might be wrong, but we're going to talk as if it's right. That's what hypotheses are usually set up to be written as if they were right, but sometimes they're not. That happens all the time. So we're making the prediction that we'll see a decrease in height in centimeters. Now, maybe I'm right, maybe I'm wrong. We don't know. But I said decrease here. You might have made the hypothesis, oh, I think it's going to increase. But again, number 3 is where you put your prediction. And again, you can see what I'm measuring, height in centimeters, specifically after, say, 12 weeks of growth. And if I was to be more specific, I might tell the species of plant that I'm using. So I might say compared to the species of, some kind of plant, same plant grown for 12 weeks in high quality soil. That would be my control or comparison group. And it comes off as wordy. Yes, I recognize that. Don't tell your English teachers. But when you actually see this written out on like an actual scientific paper, most hypotheses come out as actually rather run-on sentences. So this is all the same thing, just as one long sentence. And again, all together it sounds like this. If soil quality affects the rate of plant growth, then by growing a plant, again, you might be more specific with what kind of plant, but then by growing a plant in a pot of low quality soil, this will result in that plant having a decrease in height in centimeters after 12 weeks of growth compared to the height of the same species grown in high quality soil for the same 12 weeks. Again, it comes off like a run-on sentence, but you are very clear. What do I think is affecting what in the first sentence? What am I going to be changing in that second part of the sentence? What will the change cause? What effect will it have in that third part? And how I'm going to be measuring that. And then compared to my control groups, my baseline, how am I going to know that there's actually been an effect? So the reason I like that blended hypothesis is because it makes the rest of this very, very easy. So when we talk about variables within a experiment, variables are anything that can potentially change. We don't always want them to, but they can potentially change. So you get this issue with students not knowing the difference between these two types, what we call the independent variable and the dependent variable. So the independent variable, or it's sometimes called the manipulated variable, but the independent variable is the thing you are changing for your experiment on purpose. Really, there should only be one thing that you're potentially changing. So we'll talk about the previous hypothesis in just a minute, but again, sometimes you can change it to a degree in certain things. So for instance, if you're doing an experiment on music and your independent variable is volume, that is, say you're changing the volume, you might have several trials where you have the volume at really, really low, and then medium, and then really, really high. So you can change it more than once, but you shouldn't change anything besides the independent variable. So in that example, you shouldn't change anything besides the volume, for instance. That would be the only thing you change in the entire experiment. So to figure out what an independent variable is in any experiment, just ask, what exactly is being changed? How are they changing? What's being changed and how are they changing it? That will give you the independent variable. And that's in contrast to this thing, the dependent variable. This is also called the responding variable. And personally, I like these two names in parentheses better. It's just the textbooks like independent and dependent. The dependent variable is what you're actually measuring from your experiment. What are you measuring? How are you measuring it? Are you measuring it in seconds, centimeters, inches, pounds? Number of occurrences. Technically, that's it's not a unit, but that can occasionally happen. How often did something occur in a given time span? Miles per hour. That's a speed. So what exactly are you measuring from your experiment? Be specific. The more specific you can be, the better off you are. So if you're measuring speed, tell the units. Is it kilometers per hour? If you're measuring weight, is it kilograms? Is it pounds? Is it grams? If you're using time, are you measuring in seconds, minutes, days, hours? What are you using? So whatever you are changing, that's your independent variable. Whatever you are measuring, that's your dependent variable. And so for this example, I'm using that exact same hypothesis I did a few slides ago with the blended hypothesis format, where we're talking about soil quality affecting the rate of plant growth. And again, for our independent variable, we simply have to ask, what exactly is being changed? How are we changing it? And again, that should be right there in line 2. Well, what are we changing? We're changing the soil quality, and we're going to be lowering it. So that's the change we're making. We're lowering the quality of soil that the plant is growing in. And when we want our dependent variable, what do we ask? We ask, well, what are we actually going to be measuring? And we said it right here in the third line. We're going to be measuring height in centimeters of the plant after 12 weeks of growth. So those two questions right there tell you your independent, what you're changing, and your dependent, what you're measuring. So let me go forward on this. Again, you would change the type of soil quality here. You're decreasing the soil quality to be very specific. That's your independent variable. You're recording the plant's height in centimeters after 12 weeks of growth. That's your dependent variable. And again, the more specific you can be, the better off you are. The better off you are understanding what's going on with the experiment. If you're being vague, if you just say, we're changing the soil, it's like, well, what about the soil are you changing? Or if you said, we're measuring growth, well, what exactly are you measuring? Are you measuring number of leaves? Are you measuring diameter? What are you measuring? And when are you going to measure? How often? So the more specific you can be, the better off you are. Now, let's clarify the different types of trials that can happen in an experiment. In any experiment, if it's at least a decently designed one, there should be multiple what we call trials, multiple runs in some cases. The specific trial of your experiment that you actually have the change where you are curious about things, where you expect something to happen differently, that's what we call the experimental group. The group where you are actually, the trial I should say, the trial you are actually curious about. And that's the key question. You have to ask yourself, what trial are we actually really curious about, where we've actually changed things on purpose, where we've messed with the independent variable? That's our experimental group. And you can see this little picture here. Again, I'm using that same basic blended hypothesis example from before, so I haven't changed it. So between these two trials, which one are we actually curious about? That would be this one here. This is our experimental group, because this is the one our hypothesis really focuses on. So experimental group, what trial are you actually curious about? And again, if you're looking at somebody else's experiment, what trial were the researchers curious about when they did their experiment? That's where you want to focus to find the experimental group. In contrast, the control group is where you run a parallel trial, another trial of the same experiment, but where you haven't messed with anything, without the independent variable. Well, so you haven't changed anything in what you're testing. This often gives you a comparison. So when I said in our initial hypothesis right here that we expect to see a decrease in height, well, a decrease compared to what? Well, that means you have to run the experiment another time, a second trial, where you don't have the unhealthy soil, but you actually have the plant in either normal or what you would call healthy soil. And that gives you a comparison. That's what we would call baseline. So that's where this phrase comes up. So in this case, the control group is this trial here. This is going to give us a baseline to see Well, did this experimental group's height decrease, or was it the same, or was it taller? This is going to give us a comparison, because oftentimes you need to have some kind of comparison. You have to have an experimental group and a control group. And again, the control group is where you haven't made any changes. You just run your experiment the way it would normally occur if everything was held basically the same. I mean, it's not always 100% true, but basically where you haven't messed with anything. So I like this graph because it also kind of plies out a little bit an understanding why we do a controlled versus experimental. You can see in this experiment, and you can read this, this is about a medical experiment. You don't have to understand all of this though. But you can see from the graph of the experiment, there's a control group right here. There's an experimental group right here, and that within each one of these trials, there was a before sequence and an after sequence. So there's before something happened and then after something happened. And if you actually read here, you'll read what it's about a little bit. But you can see in the control group that when they didn't mess with anything and they had some occurrence happen, their values dropped. So that tells you whatever is going to happen, the values are expected to normally drop. In this case, it will drop from 12.1 to 9.8. So we expect a bit of a decrease under normal situations. Then on their experimental group over on this side over here, they had a drop as well, but whatever they changed, and if you read you read the thing here, you'll see that they actually changed the different type of solution, the different type of liquid they were using. They used sodium hypochlorite in this experimental group here compared to salt water. But whatever that effect had, it didn't just drop a little bit. It dropped a lot more. And so you can see that, when they made that change, they can tell, well, there was going to be a drop anyway. Yes, your control group shows that. But when you mess with this other factor, that drop is going to be hugely more significant compared to the original starting point. And yes, they don't have the same exact starting point between these two factors here, the control and experimental group, but that's where you get into statistics. Is the drop here to here, as big or bigger or less than the drop compared to here? So you can see that in the case of the experimental group, the drop is much more significant. But you wouldn't be able to tell that just by saying, oh, it's going to drop, from your hypothesis, because it's going to drop anyway. That's why you needed a control to tell you, oh, it's going to drop normally. But in your experimental group, this was really a lot more significant overall in comparison to the values. All right, so let's talk about constants. Constants are not control groups. These are different. These are things that you expect in each of your trials to remain the same. So every factor in your experiment that you're not messing with at all, that you're not measuring, it's what must always be kept the same. So going back to our soil quality and our plant growth thing, let's ask ourselves, between our two trials here, and you ideally want to run more than two, but if you were just doing these two trials, what exactly would you want to stay the same? And again, I kind of mentioned one of these in the hypothesis already. When you're talking about what you want to keep the same between the trials of your experiment, the different runs, in this case, well, the plant type. You want to use the same species of plant. You don't want to be comparing a grass that will grow really fast compared to a really slow-growing flower or something. So you want the plant's species, the plant's age to be type. If you're using plant food in the soil, you want that to be the exact same from the same source. Plant food is really just vitamins, by the way. It's not really food, and plants are photosynthetic. You want the same amount of water from the same source, same amount of sunshine, so more or less same location or place in a room. The same time for the experiment. I mentioned that in the hypothesis, that we would be recording the height after 12 weeks. And I also mentioned that you should be using the same species of plant. So I did mention two of those. I referred to two of those briefly in the hypothesis, but those should all be kept the same. If any one of those are changing outside of our control, then there's the possibility that one of those is affecting plant growth somehow. And that's not what we want to test. We want to test, does the soil quality affect plant growth? So we keep all these other items constant, hence the name constant, so that we really know there's only one significant difference between the two, and that's our independent variable. So hopefully that's narrowing it down to just one possible cause. So it shows just one possible cause. So now we're going to take a look at the end tail of any experiments, what we call the results versus what you would call the conclusion, the what versus the why. The results are the actual data you pulled from the experiment. So what did you actually observe occurring? You can use graphs and tables to show this, but this must be factual information that anybody could see by looking at your table, looking at your graphs, and say, okay, this is what was actually this is what was measured, this is what what data was collected from the experiments. You could use words like trends like increasing and decreasing if you're using a graph. This is why we like graphs. You can see trends easier that way. And so you're stating what's happening, but you're not trying to state why you think things are happening. That's going to come later. For right now, it's just the what. So to illustrate this, I have this little graph here that I like. This is showing on the y-axis number of emails, and that's from the teacher to the student per student. So coming from the teacher to the student. And then on the x-axis, you can see letter grades. Going from F up to A, and you can see it's labeled letter grades. And then I want to focus on this upper part here. You can see there's this line. And you can see right about here, if you are an F student, you get about 2.5 emails per semester, and that's in comparison to, say, an A student who gets, basically nothing, no emails from the teacher at all. And you can see that this line shows this trend that is decreasing. I'm not stating why it's decreasing, I'm just stating that the trend decreases as your grade gets higher. So the number of emails per student goes down the higher the letter grade is. That's not explaining why it's going down, what's causing it, just that's what occurs. Just the facts, nothing else. Why that occurs, that comes in your conclusion section, which comes next. That's the why section. So for right now, this is the what, the why is the next one. So let's deal with the why now. Again, the why comes from the conclusion portion of your experiments. Why do you think things were happening the way they did? You must make it clear, however, if you think your original hypothesis was either supported or rejected by the data. Never say the word proved. Now, don't trust any scientist who says something has been proven with just one experiment. It's very hard to say something is proven. You can say something has a good body of evidence to support it, but you can say there's good amount of consensus, but try to avoid that word at all costs. We really shouldn't use that word as much as we do, because there's always the possibility that there's something else going on you just don't see with a single experiment. So you can say your hypothesis was supported or rejected. That's fine. Use that. Never say proved. In this same graph, though, again, we saw this decreasing trend. Let me get my pen here. So again, the number of emails, remember, was decreasing as the letter grade goes up. And maybe now is where you state, well, let's think about why that might be. Why would the number of emails from the teacher to the student decrease as letter grades go up? Well, that's, of course, probably because, and again, I'm theorizing here. I'm not, this is a conclusion. This is not, a certainty. This is not a fact. That the number of emails, go in the reverse is higher for these students here because, well, they have a letter grade. They're the ones who are not doing what they should be doing, thus the teacher is concerned and actually wanting them to do better. Whereas the students who have A's at the far other end of this, they're getting almost no emails because they don't need any type of communication. They're doing fine as they are. So that's a conclusion based upon this data. Maybe it's right, maybe it's wrong. Maybe it takes another experiment to support this with further research. Maybe another experiment comes along and rejects that after doing a different type of research on the same topic. But never say proved, all right? Your hypothesis is either supported or it's rejected. Don't be too disappointed if it gets rejected. That happens all the time, but it's never truly proved. Remember, that idea, though, that hypotheses can easily, in many cases, turn out not to show what you're expecting them to show. There are absolutely no guarantees, and that's one of the key takeaways in all science. There's no guarantees of finding what you expect with your experiments. In fact, most scientists will tell you most of the time their experiments turn up very much not what they were expecting. They turn up very little. failure and revisions are a common fact of science. You have to get okay with the idea that your hypotheses are going to be proven wrong, rejected. They're going to be rejected more times than they're going to be supported. But that's actually a good thing. That's how we learn more in science. You're not expected to get everything right your first time. Nobody does. And you will always learn more from a rejected hypothesis than if you were to get your hypotheses right 100% of the time. Again, nobody does that in reality. In most cases, you're going to end up with failures most times. But as you build upon your knowledge and say, oh, this doesn't cause this, but maybe there's something else going on, you get closer and closer to actually seeing what cause-effect relationships we can discover. So the rejections actually become a learning process, and that's where you get into the scientific method of revision and redoing and changing things around and trying it a different way. And you can look at this through the quotes of scientists and inventors. I'm using Thomas Edison here, who will tell you failure is not a roadblock. It's actually a stepladder to finding a much better way to do things, a much more correct way to do something. So you can't expect that you're going to be right all the time. Don't assume you are. You'll learn a lot more when you actually fail than when you succeed. So just keep that in mind. Failure is expected. That is, and I'm not saying failure in understanding science. I'm saying failure in that your hypothesis won't work the way you expected. But that's how you learn about things. That's how you discover new things. That's how you get closer to getting to what we consider to be a true cause-effect relationship and understanding things that are much more complicated than we usually expect them to be. So just remember, you have to be okay with the idea of failure. That's going to occur. Don't let that, knock you down. You're going to have that happen with every single, scientist that has ever been. They've all had hypotheses that turned out to be completely and totally wrong. Nobody gets it right 100% of the time, and you'd be lucky to consider yourself right 50% of the time, and I doubt anybody does that well. So just keep that in mind. So that's going to wrap it up for this lecture on scientific experimental design and observation versus inference. We will practice a lot more with that four-step hypothesis, that blended hypothesis in class, so don't worry if that seems a lot to you. We will practice with that more. But we will look at also independent variable, dependent variable, control groups, experimental groups, and all that other stuff. Just keep in mind those questions that I gave you for how to pick those out of any experiment that is given to you. If you have any questions, though, ask me in class, and I'll see you guys then.